Now that we know how data lives in RAM, let's measure how efficiently our code interacts with it. Time complexity measures how execution duration scales with input size, while space complexity evaluates the total memory footprint consumed by the algorithm during runtime operations. As datasets grow from thousands to billions of records, inefficient algorithms cause crippling slowdowns and memory exhaustion, making complexity analysis essential for production software engineering. Big O notation mathematically describes the upper bound of an algorithm's growth rate, stripping away constant hardware factors to focus purely on input scaling behavior. O of 1 operations execute in constant time regardless of input size, such as accessing an array element directly via its memory index offset. Linear time complexity occurs when an algorithm must inspect every single element in a collection, meaning execution time grows proportionally with input size n. Nested loops create quadratic time complexity, where each element triggers a full secondary pass, quickly becoming unmanageable as input size increases. Logarithmic complexity halves the search space with every step, characteristic of binary search trees, where data remains sorted in memory. When calculating complexity from source code, we count primitive operations like assignments and comparisons while ignoring hardware constants and minor lower-order terms. Space complexity calculates auxiliary memory required by variables, call stacks, and dynamic allocations, ensuring applications do not trigger out-of-memory crashes. Recursive functions consume stack memory proportional to recursion depth, making deep recursion prone to stack overflow errors if space complexity is ignored. Engineers frequently trade memory for speed, using caching and memoization to replace expensive recalculations with fast O of 1 memory lookups. Big O evaluates worst-case scenarios to guarantee upper bounds, but analyzing best and average cases provides a complete picture of real-world algorithm performance. Amortized analysis averages the cost of operations over a sequence, proving that occasional expensive operations, like dynamic array, resizing still yield efficient overall performance. Comparing sorting algorithms reveals clear efficiency boundaries. Bubble sort runs in quadratic time, while merge sort and quicksort achieve efficient log-linear performance. Linear search scans every element requiring O of n time, whereas binary search requires sorted memory to locate targets in logarithmic time by discarding half the dataset instantly. Beyond algorithm variables, runtime environments add memory overhead for object headers, garbage collection metadata, and pointer references during execution. Theoretical complexity is verified using profiling tools that measure real CPU instruction counts and actual RAM allocation during live test runs. Unintentional nested loops and redundant database queries inside iterative routines are common anti-patterns that silently degrade application time complexity. Advanced optimization techniques like in-place sorting algorithms reduce auxiliary space complexity to O of 1 while maintaining optimal log-linear time performance.